Today we're going to create an assembly program from scratch. We're going to make a Fibonacci loop. This is going to be a scratchpad assembly program. There will be little optimization or anything of that nature to begin with. We're just going to go over the basic structure of a 64-bit assembly program. However, most of what we cover will be applicable to other assembly languages with some syntax changes. We're going to go through a basic walkthrough of what it does in a debugger. And then this will be the basis of representation for some of the future topics we're going to talk about. So to begin with, this will not be a completely standalone assembly program. We're actually going to wrap it with a C program. And I've copied this method from Randall Hyde's The Art of 64-Bit Assembly, which is an excellent book. I highly recommend you read it. But he provided us a very convenient program to wrap our assembly functions with so that we don't have to do all of it ourselves straight down in the assembly. So you can see here, if you have any experience with C, this will make a lot of sense. But the asm main function is what we're going to be doing all our logic in, the Fibonacci loop. And then it will essentially call the getTitle function, which we'll also write in assembly. It's going to call our Fibonacci loop, and then if there's any issues, it's going to let us know without us having to write the error handling into the assembly itself. Okay, so let's start writing our program. The first thing we're going to want to include, and we'll go through this more in depth step by step in the next video, but the first thing we're going to want to do is tell it that we want this to be case sensitive. So we're going to give the case map to be none. So this essentially determines whether something like Blue Mountain is the same as Blue Mountain because it's case sensitive. So those would actually be two different variables, right? Our new line is going to be 10. So now we're going to want to declare the constant portion of our assembly file. Now, you don't have to do it up here, but I would like, I just wanted to declare first. So these should never change. There should never be a call to the constant section with anything that will change the value. This page is protected, so it will throw false if you try to do that. So the title string that we're going to use, remember in here we have the getTitle function, so we want to print something out there. So our title string is going to be, we're going to declare as a byte size. And our title string is going to be fib sequence. And then later we're going to want to print what the next number in the Fibonacci sequence was. So we'll go ahead and provide that as well. We'll call it fib print, another byte. Now, if you are familiar with C, you'll notice the %d is familiar, and that's because this is what we'll actually be providing to the printf function. So this will be argument 1, and then our second argument that we will load in will be the number. And when we load in the number, it's going to take the place of that %d. Okay, now we want to load our data section. And our data section is going to contain the things that we want to change, right? So we'll declare our variables, but these will be changing over time. So we'll have our first integer. We'll declare this as a D word, and we'll make it 1. The Fibonacci sequence starts with 1. So our second integer, we'll declare another double word, and we'll make that 1. So the first number we're starting with is actually not the first in the sequence, but it is the second, I believe. Let's see here. Third. We'll be starting with the third number in the sequence. Okay, and then the end result being the Fibonacci number, we're going to declare that as well, and that can just be 0. Because we'll be calculating that. And then we're going to declare the max integer we want to go to, because at some point we will overflow. Now we're going to introduce a logic error here, and we'll fix this in a later video. but this is a later Fibonacci number, the 28th Fibonacci number. Or I'm sorry, 29th, starting at 0. Okay, and now we want to get into our actual code section. So for our code section, we are going to want to define the external function printf. Which is a procedure. And then because we're going to use that later to print out the numbers. And then now we're going to want to program our getTitle function. Remember, our getTitle function is going to be called by the C program, the C wrapper program, right here in its main function, setting the pointer of title equal to the result of our getTitle function. So the first thing we want to do here is declare this as a public function. This is important because we're calling it from a routine not within this program. So it has to be addressable by another program, which means it needs to be public. It could also be private, which means you can only call it from within this function, or within this program, excuse me. The first thing we want to do is we want to put the effective address of the title string, which we've declared up here, into the register RAX. So we're going to load the effective address. Remember, usually in assembly, it goes destination source. So the destination is RAX, and the source is the address of the title string. The reason that we can't hard code that is because we don't know where it's going to be in memory. So we load the effective address. So then once we return, we're going to hand control back to the C wrapper program. With the address of title string in the RAX register. So here we're going to be setting the address of the title equal to what the result on the RAX register was. And the ret call is just to return control back to the C wrapper. And then we'll just close this out. End procedure or end P. And then now we're going to start on our main function, the Fibonacci sequence. So again, this will be a public function because we are calling it from the C wrapper right here. So ASM main needs to be a public function. We're going to declare the procedure. And now we're going to do shadow stack. So we're going to subtract from the stack register 56, and we'll explain this in another video as well. The first thing that we want to do is move our max integer into a register. We will get into preserved registers and volatile and non-volatile registers in a later video, but for right now, we're going to want to load up our register of choice, which for us is going to be R14 with the max integer. Now, this conceptually is correct. However, we cannot use a source and destination of different sizes. So we actually need to address the first 32 bits of this register. So we need to append it with D. So now we're going to make a label, and a label allows us to jump to a particular portion of a function or a program and do something there. So these are kind of like more advanced control instructions than you have in higher level languages. So we're going to call this the next Fibonacci number. And then this is really where the core of our logic is going to be. So we need to do a couple of things. We need to get the first integer into a register. We need to get the second integer into a register. Then we need to add them together to get the next Fibonacci number. Then we need to preserve one of the integers, and it's up to us which one, but it needs to be the larger one because The way that Fibonacci numbers work, right, is let's say you have 1 and 1. You're going to add them together and you'll have 2. And then to get the next number, you'll add this last number here and then this number here. So you'll add 1 and 2 and you'll get 3. And then you'll add 2 and then you'll get 5. And then you add the 3 and you get 8, and so on and so forth, forever. So we need these first two numbers, the next Fibonacci number, and then whichever one of these we decide to have as the, we'll call it the trailing greater number. So we're going to choose EDX for our first integer. RDX would be the 64-bit, but because we haven't chosen large enough numbers, we need to address the lower 32 bits. So and then we're going to want to move into, we'll use ECX, the second int. Now we want to add them together. And because the lower 32 bits of EDX and the lower 32 bits of ECX have already been loaded with the numbers, we can add their 64-bit components together. So what'll happen here, right? So if there's 1 in first int, we're moving 1 into EDX. If there's 1 in second int, we're moving 1 into ECX. Now we're adding them together. So when we add these numbers, we'll take this number plus this number, and it'll go into the destination operand. So RDX will now have 2. And then we're going to have a problem, because if we keep overwriting this, let's say we went through another loop, so we call ourselves back up to here. RDX has 2, and RCX has 1, we'll get 3. And then if we call that again, because there's still 1 in here, EDX will have 3, ECX will have 1, we'll get 4. So we're going to have a problem unless we use another register to preserve what that sum was. So actually up here, we need to move RDX, we need to preserve RDX into the register. So we'll use R15. So R15 RDX. So here we're moving the value of RDX into R15, and then when it's overwritten in this step, because whatever RCX plus RDX is will overwrite RDX, we have that number preserved in R15. Now, once we're done adding, we want to move those back into memory, right? Out of the registers into memory. So the first thing we want to do is move EDX now into first int, because EDX will now contain the new Fibonacci number, the next one. So move first int, and we'll put EDX into that. Oops. Then for the second integer, we want to move R15, because remember, R15 is what we preserved the previous value of EDX in. And because of the memory size of second integer, we need to move, it's only a D word, we need to move the lower 32 bits. We can't move the full 64 bits. So now we want to print that. And so we want to say, okay, the next Fibonacci number we found was whatever was in EDX. So we haven't gone over application binary interfaces yet, but essentially they work like this. Whenever you have a C function, you will have a certain number of arguments, right? So you would have like func1, you'd have like int arg1, and like, character arg2, and so on and so forth, right? So in assembly, and it's true in C too, but you're much more exposed to it in assembly, you have an application binary interface. For most Windows functions, the first argument goes into RCX, the second argument goes into RDX, And then R8 takes the third, R9 takes the fourth. The rest you have to put onto the stack. And we'll go over how to do the stack arguments in another video. But for now, if we wanted to call printf, for example, the format string for printf would go into RCX. The value that we want to provide, the first value we want to provide to the string will go in RDX. The second value, if we wanted to provide more, would go in R8. The third would go in R9, and so on and so forth. So we want to put the fibprint string into RCX, RCX is the first. And then we want to put whatever is going to go in %D into RDX. So come down here and we'll load the address of fibprint into RCX. And then because we chose RDX for adding, which we did on purpose, we will already actually have the Fibonacci number in the second. So we don't need to do anything else here. We just need to call the printf function. Now we will have printed that out to the screen, and we want to compare our current number compared to our max number. So we will compare our current number. We're going to use R15. That's actually going to be an issue, but you'll see why in a little bit. Or actually, that'll be another video with R14. And then this is where we would make this recursive, and we would call ourselves again. But what do we do when we've hit our max integer? So now we need another routine. So for our end routine in this program, it's going to be pretty simple. We'll just call it end routine. And then we're going to add that 56 that we had removed from RSP when we first start the function right here. We're going to want to add that back because we want to restore the stack to the way it was before we started tampering with it. And then we'll just want to return control. So here we are going to want to, if the number in R15 is greater than or equal to our max integer, 317,811, if whatever's in R15 is greater than or equal to that, we're going to want to jump to the end routine. If it's less than that, we're going to want to do this sequence again. So we'll use the jump if less than next fib number. And then if it's greater than or equal to, we'll jump if greater than or equal to the end routine. Now to actually kick off hitting this fib number, we are going to want to jump to our next fib number. So quickly, before we step into the debugger, this is what's going to happen. We're going to start our code. We're going to essentially, make the get title string. We're going to load the effective address of title string, the memory address, into RAX. So RAX will contain the address of the memory that contains our title string. And then we're going to return the control to the C program. The C program is then call print on our title, and then it's going to call as some main. Now remember, this is a pointer, and so the pointer points to the location in memory. So we're actually setting the location of title equal to the result of RAX. So we don't actually want to return a string, we want to return an address. And then we're going to call as some main. So in as some main, when we start, we're going to handle the stack properly, which again, I will show you how to do that. Then we're going to want to move our maximum integer into R14. Then we're going to start our loop. So we're going to jump to the next Fibonacci number. We're going to move our first int into EDX, our second int into ECX. We're going to move a copy of EDX into R15. And then we're going to want to add RCX to RDX, and RDX will then contain the sum of those two numbers. Then we're going to want to move RDX back into memory, which is where first int is. And then we're going to want to move R15 into the second int memory address. Then we're going to load the effective address of our fibprint string, the next number, into RCX, which is the first argument. The second argument we already have because it's an EDX, and that will be the %D here. And then we're going to call printf, which if you used any C or even some Java or C# stuff, you'll be familiar with printf. Then we're going to compare R14 and R15, which will set a flag. Then we're going to, and we'll go over flags in another, that's a very large topic. And then we're going to jump if less than to the next fib number. So this will repeat over and over and over until the R15 is greater than or equal to our max number, which is 317,811. And then when it's greater than or equal to that, we're going to end our routine. Now we need to actually close out the assembly program itself. So we're just going to declare the end of the function and then the end of the file. This means that there's no more sections, no more data or constants or anything like that that's going to be declared. And we've made a mistake here, or I've made a mistake here. I did not declare, after declaring public here, the procedure of get title. So we want to declare that real quick. And now we are going to compile this. So again, I've copied this from Randall Hyde's The Art of 64-Bit Assembly. He's a fantastic author. He's written a lot of books on low-level programming. This is the 64-bit native tools for Visual Studio 2019 Community Edition. And I'm just going to build the Fibonacci loop. And now it's built. And so if we call the resulting program, you can see that our Fibonacci calculator works. We should have included a space here. Now you'll see that there's actually an error here. It's a logic error, not a program error. We said that our max integer should be 317,811, and yet we calculate up to 514,229, which is the next number. The reason for that, and we'll get into some more issues about that in the next video, is that we are only comparing our max integer right here. Our R14 has our max integer, R15 has the integer we're comparing. We put RDX into R15 before we do the next addition. So when we come down here, the argument actually already contains the next Fibonacci number.